Hello, this podcast is going to be an introduction to gases and also an introduction to the concept of pressure. All right, first let's talk a little bit about some characteristics of gases. First thing, gases expand to fill their containers. So if you take the lid off the container, they will expand to escape the container. They are fluid, they do flow over one another. They have a very low density. That means that they are very, very spread out as compared to solids and liquids. They are compressible, so we can force the molecules to get closer. And then they also effuse and diffuse, which we will talk about in a later podcast. All right, ideal gases. Ideal gases are a special category of gases. They're actually imaginary, none really exist, and they're important because they fit all the assumptions of the kinetic molecular theory. And some of these assumptions, as you will see, don't occur at extreme pressures or extreme temperatures. All right, gases consist of tiny particles that are relatively far apart compared to their size. So they're very small and they're very far apart. The collisions between gas particles and between the particles and the wall of whatever container they're in are considered to be elastic collisions when we're dealing with ideal gases. That means we have no loss in kinetic energy. Now, this is where real gases kind of fall short, is we know that there's going to be some sort of kinetic energy loss, even though it would be very, very minuscule compared to the system overall. Some other assumptions of the kinetic molecular theory that ideal gases follow are that gas particles are in constant rapid motion, so they possess kinetic energy. There are no forces of attraction between them. They're so far apart, they're not going to be able to have a lot of forces of attraction like hydrogen bonding and stuff like that. And then their average kinetic energy is going to depend on the temperature, not on the actual identity of the particle. All right, this leads us into our discussion of pressure. Pressure is the force per unit area. Gas molecules fill the container, and they move around and they hit the sides and they hit one another. The collisions between the walls of the container and one another are the force, and then the actual container it's in is the area. So that gets us our force per unit area. We can measure this with a barometer, or by other means. All right, let's talk about some units of pressure. So up here we see we have lots of units of pressure. They're all a little bit different though. So we have 1 atmosphere, which we'll commonly see abbreviated as ATM, is equal to 760 millimeters of mercury, is equal to 760 torr, is equal to 101,325 pascals, which is 101.325 kilopascals, which is equal to 14.7 psi, which is pounds per square inch. So we can use all of these that are equal to one another to make conversion factors to help us get into the correct units of pressure. So we'll look at this first little example problem. We have 724 millimeters of mercury. Okay, so this is just like moles. Oh snap, hold on, hitting buttons. Oh, what did I do? Y'all gotta be patient with me for a second. I gotta try to fix it. There we go. Alright, let's go back full screen. Alright, so we had our 724 millimeters of mercury. So this is like moles you have to put, which you're trying to cancel on the bottom. Why do I keep doing that? For whatever reason, I keep hitting this little button. All right. So up here we see that we have 760 millimeters of mercury. That's part of our conversion factor. All right, and we want to find how many kilopascals. So we're going to put the conversion factor for kilopascals on top. Okay, so that means millimeters of mercury went away. So all we do now is multiply and divide. And we get 458 kilopascals. Okay, all right, what about torr? All right, well, torr, see, we still start with our original amount. Okay, and again, we're going to use the conversion factor for millimeters of mercury on the bottom. And on top, we're going to put torr. Well, torr happens to be the exact same as millimeters of mercury. So really, we're multiplying by 1. So for torr in millimeters of mercury, you can pretty much just change the unit because they're equivalent. All right, and then the last one, atmospheres. So we start back with our original amount. All right, and then we've got our millimeters of mercury. All right, and atmospheres. Up here we see 1 atmosphere. So we're going to put 1 ATM. Okay, made millimeters of mercury go away. So now we have 724 divided by 760, and that gives us 0.953 ATM. Okay, and that's it. That's all there is to it.